like to motivate this with an example. So consider there's a car, okay, and it starts at x equals 0. And then you can basically drive the car, and you can, well, this is moving in a straight line, so there is no direction control, but you can speed the car or slow it down by braking. So start here and here, where this distance is d. Okay, so at some time t equals capital T, you end up with distance d, and then controls are you can accelerate or you can brake. Okay, so that's just a high-level description of the problem. Let's try to write it down in terms of equations. Okay. So first of all, I need to tell you something about how the dynamics of the cars are defined. So this is going to be very simple in terms of dynamics. The acceleration is simply u, where a equals x double dot, or the acceleration, and u is the control. Okay, so let's say that u goes between -5 and +5. So when you go with a positive value for u, you essentially accelerate, and when you do a negative value, you decelerate. So what I can do is I can write this as x double dot equals u. Okay, so that's the system dynamics. Okay, so now let's start with formulation. So before we can use mathematical tools, we need to be able to formulate the problem. So here, what I'm interested in is, and this is really subjective to, depends on your goals of the problem. In this case, let's say that we want to go from start to goal in, so go from start, that is x equals 0, to the goal, which is x equals d, in minimum time. So here we're minimizing the time. So what we can do is we can formulate the problem as follows. Minimize tt, where time t goes from 0 to t. And this is actually, you can write this as t itself. I just wrote it as gt, just to be very general. And then what are the constraints? Well, the constraints are, well, there is this dynamics, right? And we don't really write a second order system. We would like to write a first order system if possible. So this is a standard trick which is used in controls, which is you break down a second order equation into two first order equations. So that's done this way. Let's define a variable x1 for position and define x2 for velocity. So x1 dot is nothing but the velocity, because it's the rate of change of position. So we can see that that's simply x2, which is the velocity. And then x2 dot is the rate of change of velocity, which is, by the way, the acceleration, which is u. So you can write x double dot, or you can just write it as x double dot equals x2 dot equals u. So that's the system dynamics. We also define controls. So the control can only go from -5 to +5. Okay, so the control is finite. And then we have some bounds on the state. We want the position x1 at time t equals 0 equals 0. So it starts with at position 0. The position at time t equals capital T equals, in this case, d. And let's just give some value for this so that we That's how we'll solve this. Let's just put, say, 5, okay? 5 meters or 5 kilometers, whatever you like. And then x2 is the velocity at time t equals 0 is 0 because we are starting at 0 speed. And then x2, which is the velocity at time capital T, equals 0, which means that we need to come to a complete stop after time t. Okay. So now what we are left in is we need to define the variables which we are trying to optimize. Okay. And those go right below the minimization. So we are trying to find t, clearly the total time it takes. We are also trying to find the controls u. Okay. Everything else is sort of defined for us. So this is how we took the problem formulation in words and we broke it down to math. So this is the formulation. Okay, so first step is to write this. Without writing this, don't rush into programming. This is a very common mistake which people make. They rush into programming and then they do errors because they have not defined the problem properly. So this is how you do it. The second part is how do you actually take this uh, formulation and convert that into a program which can then be put into Matlab and you can solve it. So what I'm going to do is I'm going to talk about two methods to solve this problem. Okay, they are known as, I'll write them down a bit. But one thing I want you to appreciate is that this problem is what is known as an infinite dimensional problem. By that I mean u is, in this case, some function of time, and then what do you put for u at t equals 0.000 versus 0.001, 002, and so on. And that's just got infinitely many decisions to make because time is infinite. The division of time or discretization of time between t equals 0 to capital T is infinite. So that's why it's an infinite dimensional problem. So let me write this down. So this is an infinite dimensional problem because t has infinite values between 0 and t, and hence u of t is infinite dimensional. Okay, so think of this, the analog of this is in the world of computers is it's not a digital control problem, it's an analog control problem. Analog is when you can have infinitely many values from, let's say if your voltage in case of a mechatronic system was 0 to 5 volts, you can take infinitely many values from 0 to 5 volts. When you write this on a computer, you are stuck with a digital version of it. You need to convert that into numbers. You cannot have infinite numbers. So what people do is we take this infinite dimensional problem and convert into a finite dimensional problem. So that's formulation I talked about in a bit. And then we put that on a computer program to solve. So the trick is, and this is very standard, is to convert. So convert this into a finite dimensional problem for implementation in Matlab. Okay, in fact, for any programming language, you will have to convert into a finite dimensional problem. So the method by which the generic method which people use to solve this problem, to make it into a finite dimensional problem is is this is known as parameter optimization. Okay, what that means is instead of having infinitely many values, you convert it into finite values or finite parameters. So instead of finding controls which can take infinitely many values, we'll assume that controls. So what this means, assume that the controls have distinct values at distinct points. So for example, if we assume that the control, this is t, capital T. So if you thought the control would be like this, what we'll do is we'll actually find the values of the control at distinct points. We could also, so between this point and this point, this is a curve, right? So you could have a curve, in which case it will be something like a second or a third order, but we could also keep it very simple. We could just assume it to be a constant line. So once we find the values at these points, which is how we'll solve it, we can join these points by straight lines, or some people will do something even more simple, which is they will just put constant between those two. So if these are the solutions at different points, we just assume it just goes constant and then constant, 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 and then there's a jump. So there are two different ways of really writing this. You could have something like this, which is constant, or you could have something which is smooth. And the smoothness could be linear, it could be quadratic, third order, so on. So this is one example how we do parameter optimization. We convert the values at infinite values into finite values using some approximation of the controls. Okay, so what I'm going to show you is two ways of solving the car problem which I just described. Okay, and there are many ways. I'm just showing you two. Okay, two sort of different ways. So one is what I'll call a collocation method. Okay, and the other way is called shooting method. So car solver in Matlab. And both these methods will actually use fmincon, okay, because it's a constraint optimization. However, we need to write in terms of parameters now. Okay, so in collocation, what we do is, so let me just formulate now the problem as I would as a collocation problem. Collocation method. Okay, so what we do here is instead of so we have differential equations, and we say that we want to satisfy those differential equations at distinct points in time. Okay, and that is the heart of collocation method. So satisfy the differential equations at distinct points. So for example, if we wanted to discretize time as 0, 0.1, 0.2, 0.3, then we will ensure that the equations are satisfied at 0, 0.1, 0.2, 0.3, and so on. So the way we do this is first, or A, we have different optimization variables. So we do have capital T and U, but we would like to find U at distinct time intervals. So I'll call that U of I. So imagine there is time axis, and then we have I equals 0, I equals 1, I equals 2, I equals 3, This could be uniform spacing or non-uniform spacing. People usually use uniform spacing. So this is uh, t, t plus dt, t plus 2 dt, and so on. Right? And so we want to find the control at u of I. You know what? Let me just use I equals 1 because Matlab doesn't like 0. So let me just put I equals 1, 2, 3, 4, 5, and so on. So u of I, so u of 1, u of 2, u of 3, so on. We also need to find what x1 is, which is the position at each of these times. So x1, 1, x1, 2, x1, 3, so on. And then we are only left with x2 of I, which is the velocity. So again, we need to find x2, 1, x2, 2, x2, 3, so on till got this I equals n. So x n, x to n, sorry, x to n, x1 n, u n. So you can see that now we need to find this, all these values, and so on. So these are our optimization variables. The optimization objective is to minimize t. And then finally, we have the constraints, optimization constraints. So now what I need to do is I need to take the same constraints I defined earlier and write in terms of x11, x12, x21, x22, and so on. So let's see what those are. So if you see, go back, you can see that these were the different constraints. So let me copy this. And I'll just put it here just for reference. That way we can see what those are. Okay, so I'm going to attempt to write these down. So the easiest ones, let me write the easiest ones first. So the easiest ones are actually this one. So let me call that 1. 1, we call this 2. That's also easy, as you see. 3, 2, 3, 4, 5, and then finally we'll write this 6 and 7. So 1. So 1 just says that at any point of time, u of I, which should be between -5 and 5, right? What it means is at every instant, you cannot break more than 5 units of whatever that quantity I have, and or minus accelerate by 5, more than 5, or decelerate by beyond -5. So that's easy. The second one is saying that at time t equals 0, x1 is 0. So that's simply x1 equals 0. Okay, where x1, so x11 is x1 is the position and 1 indicates the time, the initial first time instant. The third one is simply saying that the velocity at 1 is equal to again 0. The fourth one is x1 at n equals 5. So it's the position at the final time is 5. The fifth one is x2 at n equals 0. That's the velocity 0. And now comes the sort of the harder ones, which is 6 and 7. Now 6 and 7 are true for all instances of time, unlike these ones where u of I was valid for all instances of time, but other ones 2 to 5 were only valid either at the beginning or at the end. So what we need to do is we need to sort of write this in terms of i's, x i's, x1 i's, and x2 i's. So what we do is we resort to Euler's method, right? Euler's method is basically saying that x1 dot can be written as x1 at t plus delta t minus x1 of t divided by delta t equals, in this case, x2. So what we do is we write this as x1. So t plus delta t is simply I plus 1. And I'm going to do a little bit of moving around without actually writing it down. So I'm going to move this delta t to the other side. So I would have x2 of I times delta t plus this x1 t will also move to the other side. So that will be x1, t in this case is I. And so we have this expression for all instances of time. Similarly, I can write for equation 7. Okay, I'm just going to write the answer down, and I hope you will connect the dots at home. So x2 dot is x2 I plus 1 equals x2, sorry, u. So this should be I, u of I times delta t plus x2 of I. So it's exactly similar to the first equation, the sixth one, except that I replace x1 with x2 and this x2 times delta t with u times delta t because there's a u here. Okay, so that's it. I've taken those 7 equations and written down 7 equations in this form. These are, by the way, not 7 equations. They are actually many more than 7 equations, because think of this. This I goes from 1 to n. So there are really n equations there, right? Similarly here, I goes from 1 to n. So there are n equations here too. And then there'll be n equations here. So really we have n equations. So you can just count them. N equations, 1, equation 1, 1, 1, and then n over here and n over here. So altogether we have n plus n plus n, so that's 3n plus 1, 2, 3, 4. These many equations. So clearly the finer discretization we use. So what's discretization? It's the number of discrete time intervals we have. So more the number of time intervals, the larger is the set of equations we need to solve, and the more complex the problem is, right? And so all we need to do now is to take this set of equations and write it in the language of Matlab. So what you can again do here is identify which of those equations are linear, which of them are non-linear. So let's just do that here before we put it in Matlab. Okay, I copied that, but let me write down what Matlab expects first. So I wrote this down last time. So first of all, we need to use f min con, right? Because this is a constraint optimization. So f min con expects the cost f of x. It expects the upper and lower bounds. It expects the linear constraints. It expects well, the linear inequality constraints, and then non-linear constraints. Okay, all this is what is expected. So we can now try to identify these things. So first of all, the bounds. Let's just name these 1, 2, 3, 4, 5, and 6. So this is going to get confusing with the other notation. Let's just call it 1, 2, 3, 4, 5, and 6. Okay, so it's good. It's unique. Okay, so 1, we know that's just simply the time. 2, for 2 we need to give bounds for everything. So for ui we know the bounds, so you can see that u of I between -5 and 5. But for others, so for example x1, now we know from this example that the position cannot be greater than 5 because the car has to go from 0 to 5. So we can actually put a bound. The more you can bound the problem, the more you're helping fmincon, because the smaller the things it has to check, the faster will be the solution. So if you can always give bounds. If you can't, then you can keep them as infinity. So here we're going to put infinity. Although we know that the velocity cannot be infinity. Well, okay, so you can keep this. I usually recommend putting a large value, but not infinity. So let's put 100 minus 100, and that's just made up. If after running the optimization, you see that this bound 100 is approached by the solution, that means that you're constraining the problem and you want to change that bound. So, but to start off, you can just put some meaningful bound. Okay, and then 3, the linear constraint. So if you see the linear constraints, number 2 is a linear equality constraint. Number 3 is, number 4 is, number 5 is, that'll be 1, 2, 3, and 4. Okay. In fact, 6 and 7 are also inequality constraints. So actually, my bad. This should be 2, 3, 4, 5, 6, and 7. Okay, all of them are actually linear equality constraint. We do not see x square coming anywhere. Then we have 4 is A, which is null, B is null, and C and C equals is null. Now, what I did was, and this might sound a little bit strange, which is instead of specifying all these as linear equality constraints, which they are, there's a little bit of bookkeeping involved here, because you need to make x as a big, x is going to be, this x is not the same as this x1 and x2. It's basically all the decision variables. So x here would be u, t, u, x1, and x2. So what happens is if you try to put it in that form, that x is going to become so big, and because it has all the u's and all the x and all the x1s and all the x2s. And I think there's a lot of bookkeeping involved here. So what I do is I try to avoid putting this just to make my life easy. So instead of putting them as an equality constraint, linear equality constraint, I actually put them as non-linear equality constraints. And that's just because to make my life easy. Make it easy to code. So one thing you can realize is that anything which is non-linear, so anything which is linear like this can also be put as a non-linear constraint. It won't change anything. Okay, now it will actually affect fmincon and its ability to produce a solution fast. But for all practical purposes, if we don't have a time constraint, then we can actually do that. So I'm going to put that as 6 instead of 3, although we could have written as 3. So we're going to write A equals null and B equals null. Okay, and then finally, 5th one, which is the non-linear inequality constraint, is simply null. So let's see how to program this in Matlab. Any questions? Feel free to put them in the chat or unmute yourselves.
So for x2, since we set it equal to 0, or x2 of n equals 0, why are we setting the bounds to be negative 100 and 100 instead of 0.
So actually we can put minus infinity to plus infinity. If you like, you put that. I just like to put some non-infinite bounds, because the bigger the search space, the harder it becomes for fmin con. So what I like to do is put like a bound, solve the problem, and then if you see that some of the bounds are approaching by when solution has some of the bounds coming in the solution. So let's say 100 was one of the velocity became 100. So I know that I should not have put it as 100. I should have increased it to maybe 200, and then I keep doing that. So that's just a choice you make based on the problem. If it's a big problem involving many variables, then you have better luck solving it this way. Does that answer your question?
Yeah, but so whenever there's a variable that's like set equals 0, like it'd be like x of n being equal to 0. That basically means that our bounds that we can choose from can basically be infinite, right? And I don't really like know the reason why it would be like infinity instead of having the bounds being equal to 0.
Oh yeah, so you're talking about this, right? So this one is 0, but I also have it over here. Is that why you're asking?
Yeah.
Okay, so there are ways to do this. You could actually put this inside here, and then you'll get rid of this one, and you'll get rid of this one. You can actually take this, put it over here, and take that, put it over there, and that's clearly a good way to do it. Instead of trying to bound them from 0 to 5, you just put the constraint right here. Here I'm just putting it because it is more convenient to define that way. So that way I'm not really thinking about, okay, which value has to be 0, which value has to be 5. So this adds more constraints. Okay, this is not needed if you take care, write it down. If care of x1, x2 in LB x1 UB and LB x2 UB. So it's just a preference. It won't the problem which you are trying to formulate, which has the bounds inside LB UB, essentially the same as what I have here. I have added more constraints, so it makes it hard, sort of adds more things to the optimization, but the solution would be the same. Sometimes it's a matter of convenience and bookkeeping. So you want to, I try to find a way in which I can code it faster than trying to write the minimal set of equations, if that's what you're asking. Does that make it clear?
Yeah.
And I would say the best way to learn this is, I can explain this take all the time and explain this, but you're most better off if you actually take this code down and sort of break it into parts and try to understand it yourself, because it's just so hard to tell exactly what I'm doing unless you actually see it. So what I recommend people is take a smaller number of, so n is basically grid points. By choosing small size for n, you can actually see how what I've written down translates to what I wrote down on paper. So here I made it very generic to n. I can just change the number of grid points and I'll get solutions for that. I actually also put bounds, which are 10 and minus 10, but I could put 100 and then umin and so on. So I need to give an initial guess. And so everything I set, except for time, I set to 0. Here you can see I put tmin as 1 and 3, but it doesn't have to be that. I can put whatever. I can put 5, 10, whatever you want. And then the main crux of it is to define this function fmin_con. So many things in this function are zeros, which is nice. What is not 0 is the bounds. Okay, so this is exactly what I wrote down earlier: the min and max for position, min and max for velocity, min and max for controls. And then what I did was I just made my life easy by defining the linear inequality, non-inequality, and equality constraint 0. So I have all my constraints defined in as nonlinear constraints, which are here. So this is where I think it gets really hard to understand. So what's going on here is, this code is, I'm basically trying to set the differential equation equal to 0, right? All those values inside C equals should be equal to 0 if the problem is if the solution is satisfied. So I'm trying to set the difference between position I get at I plus 1 minus the one from the differential equation to be 0. So the typical way people like to call it in this world is called a defect. Defect means the difference, or if you like, if you think this better, difference. Some people would like this one than the other one. So let me just change it here. So those are the main things. These are the differential equations. Differential equation. Okay, that's one. And then let's see. Okay, so then I specified the velocity at the start is 0. The position at start is 0 because everything in C equals has to be 0. And then I specified the position at the end equals d, and the velocity at n equals z. So everything is put compactly in this equation. And so then what I need to do is now run this. Now, before I run this, can anybody guess what is the optimal strategy is? So if you are in a car and you're supposed to go from start to stop, cover a certain distance and do it in minimum time, how should you drive the car? Can anybody guess?
Accelerate for half the time and then deaccelerate for the other half of the time?
Okay, so is that Brian?
Yeah.
Okay, that's exactly what you would do, except there's a slight thing, which is sometimes doing that will work if you have infinite acceleration available or the distance is short. If it's a long distance, then you want to accelerate full throttle and then coast and then decelerate, because you cannot go beyond certain value for the acceleration. So here is so accelerate. Can you see my screen? Okay, you can see my screen. So this position versus time, velocity versus time, and control versus time. So you go 5, and then somewhere you switch to -5, and then you stop. So here the solution comes out to be 2.010104, which is the time it takes. Okay, so if you now, so this is for n equals 5. Which is just 5 intervals, but we can change it to n equals 10 and then run this again. And then I get something like this. Looks much smoother. Okay, you can see that the graph for position actually was much smoother. And then you can do it for 20. And the more number of points you specify, the more smoother it gets. And that's pretty much what you want to do. In fact, this will become a step function once you increase it to 100, probably. Maybe it'll probably become a step. Let's try 100, which is going to take a lot of time, I think. Oh, it's pretty fast. So here it actually looks like it did not converge here. So it converged to an infeasible point. So this is what happens with any optimization, which is it has its own constraints in terms of solving a problem. If there are too many variables, sometimes it just chokes. And here it doesn't really give you the value. Let's try 50. So just because you see a result, it doesn't mean it works. So here also it doesn't quite converge there. Let me try to backtrack and get it 20 and see if that works. Okay, so this one looks like it converges. You can check that quickly. It goes from 0 to 5. Okay, so that's the collocation method. Let's stop here. Let's talk a little bit about the survey and the exam. Okay, I think everybody wants to hear this. I went a little bit over time today on